In the final years of the 19th century, when the world stood on the edge of a new scientific awakening, a boy was born in the heart of Vienna whose mind would one day change humanity's understanding of reality itself. His name was Erwin Rudolf Joseph Alexander Schrödinger, a child destined not only to unravel the secrets of atoms, but also to question the nature of existence itself. It was August 12, 1887, when Vienna's air hummed with the music of culture, philosophy, and science. The city was alive with ideas, from the art of Gustav Klimt to the philosophies of Ludwig Boltzmann. Into this world came a young soul, quiet yet curious, surrounded by a family that valued knowledge, art, and the wonders of nature. His father, Rudolf Schrödinger, was a botanist and owner of a linoleum factory, a man of deep intellectual curiosity who spent his evenings studying plants and reading scientific works. His mother, Georgian Amelia Brenda, came from an academic family. Her father was a professor of chemistry. Together they created an environment where questioning the world was as natural as breathing. In that elegant Viennese home, filled with books, microscopes, and the scent of experiments, little Erwin learned the beauty of inquiry long before he could understand its complexity. There were no boundaries between art and science in his world. His father taught him to see both the logic of nature and the poetry hidden within it. This early blend of precision and imagination became the essence of Schrödinger's mind. He grew up in a society that worshipped classical music, philosophy, and intellectual debate. The streets of Vienna echoed with the discussions of scientists and philosophers who were beginning to challenge the foundations of Newtonian certainty. Erwin listened, learned, and wondered. Unlike most children, Schrödinger's curiosity had a peculiar depth. He was not content with memorizing facts or following formulas. He wanted to understand the why behind every phenomenon. He observed patterns of light, shadows, and sound, and he felt an invisible connection among them, something mysterious yet harmonious. His love for mathematics began early, and his natural gift for logical reasoning flourished quickly. He was fascinated by geometry and physics, by the way numbers could describe motion, energy, and even the colors of a sunset. Yet even as a child, his imagination went beyond the material world. He often pondered questions about life, consciousness, and the unseen fabric of reality. By the time Schrödinger entered secondary school, he had already developed an unusual independence of thought. He was not a rebellious student, but a silent thinker, one who preferred reflection to recitation. Teachers noticed that his answers were not only correct, but original. He sought beauty in logic, elegance in proofs, and meaning in every symbol. For him, science was not a dry mechanical pursuit. It was an art of discovering the rhythm of the cosmos. His early education was rooted in both the humanities and sciences, a rare combination that allowed him to see beyond the traditional boundaries of subjects. Latin, German literature, and philosophy shaped his sensitivity, while mathematics and physics sharpened his analytical mind. This synthesis of logic and imagination would later define the very core of his scientific genius. As a teenager, Schrödinger began to read the works of great thinkers who had tried to explain the natural order of the universe. He devoured the writings of Newton, Maxwell, and Boltzmann. It was Boltzmann, the Viennese physicist who pioneered statistical mechanics, who had the deepest influence on the young Schrödinger. Boltzmann's lectures at the University of Vienna were legendary. They were filled with fire, energy, and philosophical depth. Even though Schrödinger was too young to attend at the time, the echoes of Boltzmann's ideas filled the intellectual air of Vienna. The concept that nature was not deterministic but probabilistic, that chance itself played a role in physical reality, left an imprint on the developing mind of Erwin Schrödinger. He was also deeply moved by the works of Ernst Mach, the philosopher and physicist who challenged the absolute concepts of space and time. Mach's ideas about perception and the relativity of observation fascinated him. Schrödinger began to see that science was not merely about describing objects, but about understanding the relationship between the observer and the observed. This early awareness of perception and reality would later bloom into one of the most profound philosophical positions in modern physics. When Schrödinger entered the University of Vienna in 1906, he was already equipped with a broad and disciplined intellect. The university was a temple of learning, alive with debates about atoms, energy, and the nature of light. There he met Friedrich Hase-Hurl, one of Boltzmann's successors, who became his mentor and guide. Hase-Hurl introduced Schrödinger to the latest theories in thermodynamics and radiation, including the groundbreaking ideas of Max Planck. Planck's concept of quantized energy, that energy could exist only in discrete packets, intrigued the young student, though it seemed strange and even disturbing to classical reasoning. Schrödinger, however, had a mind that could embrace paradox. He sensed that these new ideas were not the destruction of classical physics, but its transformation into something deeper. At the University of Vienna, Schrödinger excelled not only in physics but in mathematics, philosophy, and logic. His professors were impressed by his ability to move effortlessly between rigorous calculation and abstract reasoning. He had the discipline of a mathematician and the soul of a philosopher. He attended lectures, conducted experiments, and engaged in heated discussions with his peers, but his most profound discoveries often came during solitary walks through the streets of Vienna. He would carry a notebook, jotting equations, questions, and reflections on nature. He began to feel that the secrets of the universe were not hidden in laboratories, but in the patterns that surrounded life itself, in light, in motion, in the rhythm of existence. World events soon began to shape his destiny. As the early 20th century advanced, science was undergoing a profound transformation. Einstein had already published his theories of relativity, and Planck's quantum theory was beginning to reshape the landscape of physics. The young Schrödinger was living through the greatest scientific revolution since Newton. Yet, unlike many of his contemporaries who were fascinated by the mechanical aspects of atoms and energy, Schrödinger remained drawn to the idea of unity. He believed there was a deep harmony underlying all of nature, something continuous and elegant, even within the apparent chaos of atomic motion. His time at the University of Vienna was not only a period of learning, but also of internal questioning. Schrödinger was deeply influenced by philosophy, especially by the works of Schopenhauer. Schopenhauer's view of the world as a manifestation of a single underlying will resonated deeply with him. It offered a metaphysical framework that seemed to align with the continuity he sought in physics. He began to see the universe not as a collection of separate objects, but as a single, living whole. This fusion of science and metaphysics became a lifelong theme in his thinking. For Schrödinger, to understand physics was to understand existence itself. By 1910, Schrödinger had completed his studies with distinction, earning his doctorate under Hase-Hurl. His early research focused on color vision and the conductivity of air under radiation, showing his remarkable ability to bridge experimental observation with theoretical interpretation. But it was clear that his true calling lay in theoretical physics. He was not content with describing how phenomena worked. He wanted to know why they worked that way. His early papers already revealed a style that would define his later achievements: clarity, mathematical beauty, and philosophical depth. In the following years, he served as an assistant at the University of Vienna and later as a teacher. Yet his path was soon interrupted by the turmoil of World War I. The war years were a dark and uncertain time, but they also became a period of deep introspection for Schrödinger. Amidst chaos and destruction, he found himself meditating on the order hidden within the universe. He began to feel that science, like philosophy, was a way to restore harmony to a world torn apart by conflict. Even in the military, where he served in meteorological work, he maintained his scientific curiosity, studying atmospheric physics and continuing to write theoretical papers whenever he could. This experience shaped his outlook profoundly. He realized that knowledge, while powerful, could also be fragile, and that the pursuit of truth required not only intellect but wisdom and humility. When the war ended, Schrödinger returned to academia with renewed purpose. The intellectual landscape had changed dramatically. Quantum theory was beginning to take shape, and the foundations of physics were being rewritten. But before he would enter the stage of global fame, his early education and formative years had already prepared him for that revolution. He carried within him a rare combination of precision, creativity, and philosophical sensitivity, the very qualities that would later allow him to conceive of wave mechanics and the legendary thought experiment of the quantum cat. Looking back, one can see that every element of his early life pointed toward this destiny. The nurturing atmosphere of his Viennese childhood, the influence of his father's curiosity, the inspiration of philosophers and scientists, the exposure to both logic and art, all these threads wove together to form the tapestry of his genius. He was not a man shaped only by equations, he was a thinker shaped by wonder. From his earliest days, Schrödinger believed that nature's beauty was mathematical, and its truth was eternal. His education did not merely teach him facts. It awakened in him a lifelong dialogue between science and philosophy, between logic and imagination. As the 20th century unfolded, this dialogue would lead him to discoveries that would forever alter our conception of the universe. Yet even then, in the quiet classrooms and lecture halls of Vienna, the seeds of his revolutionary ideas were already growing. The young man who once gazed at the patterns of light through his father's lenses would one day reveal the hidden waves that underlie all matter. His early life was not just the story of a student learning physics. It was the story of a mind awakening to the vast mystery of existence. A mind that would soon dare to imagine the impossible and challenge the boundaries of reality itself. The war had ended, but Europe was scarred. Cities were wounded, economies broken, and the spirit of scientific progress seemed uncertain. Yet, for Erwin Schrödinger, the end of conflict marked the beginning of a new internal awakening. The silence that followed the cannons became a space for thought, for reflection, for discovery. He had seen the world at its most chaotic, and now he longed to uncover a deeper order, something constant beneath the surface of destruction. The very universe, he believed, must have an underlying rhythm, a secret music holding everything together. When Schrödinger returned to academic life after World War I, he did so with an intensity that astonished his colleagues. It was as if the years of silence had condensed into a storm of creativity. He began teaching at the University of Zurich, then later in Jena, Stuttgart, and Breslau, but each appointment was more than a job. It was a step along his search for universal harmony. He approached physics not as an isolated science, but as a dialogue between mathematics, nature, and the human mind. His lectures were quiet yet magnetic. Students remembered how he spoke of equations as if they were poetry, how he drew curves on the blackboard as though sketching the flow of life itself. During this period, he delved deeply into the works of Planck and Einstein, whose theories had revolutionized the early 20th century. But he also began to feel the limitations of classical atomic models. The universe described by Newton and Maxwell, elegant as it was, could no longer explain the strange behavior of electrons inside atoms. Something deeper was hidden in the fabric of matter. Something invisible, unpredictable, yet beautifully consistent. Schrödinger sensed that this mystery was not a failure of science, but an invitation to see nature in a new light. His education had trained him to combine imagination with precision, and now that blend began to bear fruit. He started asking questions that others overlooked. What if matter could be described not as discrete particles, but as waves? Could the movements of electrons be visualized as oscillations, like ripples on a cosmic sea? These questions were not yet equations, they were visions. Visions that came to him during long evenings of contemplation, sometimes while walking through the quiet streets of Zurich, sometimes while sitting by a lake watching the reflections of light on water. But to understand the full significance of his early intellectual evolution, one must look deeper into the character of the man himself. Schrödinger was not simply a physicist, he was a thinker who felt life intensely. He read poetry in several languages, wrote essays on philosophy, and studied ancient texts from the Upanishads to Plato. His library contained not only scientific treatises, but also works of art, psychology, and mysticism. This breadth of interest was not a distraction but a foundation. It allowed him to perceive science not as a mechanical craft, but as an exploration of existence. Every discovery for him was a revelation of unity. It was during his time in Zurich that Schrödinger's personality truly began to reflect the synthesis of his early education. His lectures bridged the gap between abstraction and experience. He would explain complex theories with analogies drawn from music or art. To him, mathematics was not dry logic but a language capable of expressing the poetry of reality. This vision was deeply rooted in his formative years, when his father's curiosity and Vienna's intellectual culture had taught him to find beauty in reasoning. The scars of war had also deepened his philosophical side. He saw how fragile civilization could be when knowledge was used without wisdom. He once wrote that science should never lose sight of its spiritual meaning, that understanding the laws of nature was inseparable from understanding humanity's place within them. This ethical and metaphysical awareness would later distinguish him from many of his contemporaries who focused purely on the technical aspects of physics. For Schrödinger, knowledge without reflection was incomplete. As he advanced through the academic world, Schrödinger's intellect became sharper and more daring. He began to publish papers on atomic theory, thermodynamics, and the behavior of electrons. Each work reflected his unique style, clarity, elegance, and deep conceptual unity. But behind the formal mathematics lay a restless curiosity, one that would soon lead him to a discovery that would redefine the foundations of quantum theory. Yet, even before that great moment, his early life had already prepared the ground for it. The blend of his Viennese education, his philosophical temperament, and his sensitivity to nature formed the perfect soil for the growth of a revolutionary idea. He had always sought patterns, invisible harmonies beneath apparent chaos, and now he was about to find them at the quantum level. The question that obsessed him was simple but profound: what is the true nature of an electron? Scientists of his time treated it as a particle, a tiny billiard ball moving under forces, but Schrödinger sensed that this picture was incomplete. Particles behaved like waves, showing interference and diffraction. Could it be that matter itself was not solid, but wave-like? This idea began to crystallize in his mind like a vision. He remembered his early fascination with sound and light waves, with the vibrations that shaped the world. He realized that the same mathematics describing waves in strings and water could describe the behavior of matter at the smallest scales. In 1925 and 1926, those reflections became the foundation of his wave mechanics, an achievement born not from sudden inspiration, but from a lifetime of curiosity, discipline, and philosophical reflection. Every equation in his theory was the echo of his early education, every insight the continuation of a journey that began in his father's study in Vienna. Even in those years of scientific triumph, Schrödinger remained deeply aware of his intellectual roots. He once said that true discovery requires seeing the world as if for the first time, with the innocence of a child and the precision of a mathematician. His childhood wonder, nurtured in an environment of learning and culture, had never left him. The same curiosity that once made him question the color of light now made him question the structure of reality. His early education had also instilled in him a love for clarity, for making the complex appear simple without losing its depth. This quality became evident when he wrote his papers on wave mechanics. They were masterpieces of exposition, elegant, transparent, and persuasive. Even Einstein admired them. But what most readers did not realize was that the clarity of those papers was the result of decades of internal dialogue, a conversation between the logical and the mystical sides of his mind. In the quiet hours of his study, Schrödinger often reflected on how his life had unfolded. He saw a continuity in it, a kind of internal symmetry that mirrored the physical symmetries he studied in nature. His journey from Vienna to Zurich, from student to professor, from curiosity to discovery, was not a random sequence but a wave, a rhythmic unfolding of thought. The more he understood the universe, the more he felt that it was not made of separate things but of interconnected patterns. His education had not merely given him tools, it had taught him to see unity where others saw fragmentation. He once wrote in his notes that knowledge is the awareness of unity in multiplicity. This sentence could well summarize his intellectual evolution. The young boy, who had been fascinated by the harmony of light and sound, had grown into a man who sought the harmony of quantum waves. His learning was not confined to textbooks. It was a lifelong act of meditation on the nature of being. Even his personal life reflected his complex mind, passionate, searching, and unconventional. He was drawn to art, music, and conversation. He believed that creativity was the essence of intelligence, whether in science or in life. Those who knew him spoke of his intensity, a quiet fire that seemed to burn behind his calm demeanor. He could spend hours lost in equations and then shift suddenly into philosophical reflection or poetic musing. This ability to move between worlds, between reason and imagination, was the legacy of his early upbringing. In many ways, Schrödinger's early education had done something rare. It had preserved his sense of wonder while sharpening his intellect. Most people, as they grow older, lose one to gain the other. Schrödinger never did. The boy who once wondered at the mysteries of color grew into a man who could express those mysteries in mathematics. The same spirit that once marveled at the patterns of nature now uncovered the patterns that governed atoms. His life was a continuous thread of curiosity. As he stood on the brink of his great discoveries, the world around him was entering another era of transformation. Quantum theory was spreading across Europe. Physicists like Heisenberg, Bohr, and Dirac were redefining the rules of nature. Yet Schrödinger's approach remained unique, less mechanical, more holistic. It was the approach of a man shaped equally by art and science, by philosophy and logic. His early life had not trained him merely to calculate. It had taught him to see. And that gift of vision would make all the difference. The rhythm of his thoughts echoed the rhythm of his times. The same Vienna that had nurtured Freud, Mahler, and Wittgenstein had also shaped Schrödinger, a city that valued depth, ambiguity, and introspection. From that atmosphere, he inherited an ability to dwell comfortably in uncertainty, to find meaning even in paradox. It was this intellectual tolerance for ambiguity that later allowed him to accept the strange duality of the quantum world. A world where particles were also waves, where existence and non-existence seemed to blend. His early education had not prepared him for simplicity, it had prepared him for complexity. As the 1920s advanced, Schrödinger's intellectual maturity became apparent to all who knew him. Yet the seeds of that maturity had been sown decades earlier, in the quiet classrooms of Vienna, in the endless books he devoured, in the philosophical musings he carried in his notebooks. He never separated learning from living. For him, the study of nature was a moral act, an act of reverence. Science was not a conquest of reality, but a dialogue with it. That attitude, that humility toward truth, was perhaps the most enduring lesson of his early education. Every great mind, in the end, is a reflection of its formative years. In Schrödinger's case, those years were filled with harmony, the harmony of science and art, of logic and wonder, of curiosity and contemplation. His later achievements were the flowering of those early seeds. The elegance of his wave equation, the philosophical depth of his cat paradox, the courage to question reality itself, all were born from a childhood spent asking not just how things work, but why they exist at all. When we look back on the early life of Erwin Schrödinger, we see more than the biography of a scientist. We see the unfolding of a worldview, one that sought unity where others saw fragmentation, one that found beauty in equations and mystery in reason. His education was not merely the learning of facts, it was the awakening of a mind destined to change the world. the boy from Vienna, guided by curiosity and shaped by culture, grew into the man who imagined the quantum cat, and in doing so, forever transformed our understanding of what it means to observe, to know, and to exist. The end of Erwin Schrödinger's formal education was not the end of his learning, in truth. It was the beginning of his journey into the unknown. When he left the University of Vienna with his doctorate in hand, he carried with him not just a degree but a worldview. A sense that nature was an intricate poem written in the language of mathematics. The early 20th century was an era of transformation. The certainties of Newton's universe were crumbling under the pressure of new discoveries. Atoms, once thought to be solid and indivisible, were revealing a complex inner world of forces and probabilities. Light behaved like both a wave and a particle. Space and time themselves were being reimagined by Einstein's relativity. Into this world stepped Schrödinger, a man whose curiosity was unbounded, whose intellect was disciplined, and whose imagination refused to be confined. In his early academic years, Schrödinger moved from one university to another, seeking both stability and inspiration. He taught in Vienna, Zurich, Jena, and Breslau, and later held positions in Stuttgart and Berlin. But behind each change of location was a deeper restlessness, a desire to find a place where thought could flourish freely. He was not the kind of physicist who thrived in laboratories filled with instruments and data. His laboratory was his mind. For Schrödinger, the blackboard and the notebook were the landscapes where he explored the universe. He lived through equations, sketches, and reflections, building bridges between the seen and the unseen. During these years, Schrödinger immersed himself in the work of those who had begun to dismantle the old order of physics. He read Max Planck's papers on blackbody radiation, where the concept of quantized energy first appeared. Planck's idea, that energy came in discrete packets, or quanta, was revolutionary, but Schrödinger found it unsettling. It clashed with his belief in continuity, in the smooth and flowing nature of the cosmos. Yet, even as he struggled to accept it, he recognized its beauty. There was something profound in the idea that nature, at its deepest level, moved in rhythm rather than in chaos. He felt that Planck's discovery, though fragmentary, hinted at a hidden unity yet to be revealed. Equally influential was Albert Einstein, whose theories of relativity and light quanta reshaped the landscape of modern science. Schrödinger admired Einstein deeply, not only for his genius but for his independence of thought. He saw in Einstein a kindred spirit, a scientist guided by intuition as much as by logic. Einstein's work on the photoelectric effect, which demonstrated that light could act as discrete particles called photons, intrigued Schrödinger immensely. He sensed that within these paradoxes, wave and particle, continuity and discreteness, lay the key to understanding reality. The young physicist also drew inspiration from the legacy of Ludwig Boltzmann, the Austrian master of thermodynamics and statistical mechanics. Boltzmann's tragic death had cast a shadow over Viennese science, but his ideas remained alive in Schrödinger's mind. Boltzmann had taught that the laws of nature were not deterministic but statistical, that beneath order lay probability, and that chance played a role even in the most precise systems. Schrödinger admired the boldness of this view, though he often struggled to reconcile it with his own longing for harmony. He was drawn to paradoxes, but he sought to resolve them, to find the mathematical melody that united them into one. The Great War had changed not only Europe, but also the spirit of science. The optimism of the 19th century, the belief that reason could solve everything, had been shattered. For many, the chaos of the war mirrored the chaos of the quantum world that was beginning to emerge. But for Schrödinger, this was not a time for despair, it was a time for new beginnings. He saw in the shifting sands of physics a chance to rebuild, to seek truth beyond the ruins of certainty. After the war, Schrödinger accepted a position at the University of Zurich in 1921. It was there, in the quiet beauty of Switzerland, that his genius began to unfold fully. Zurich was a place of peace after years of turmoil, a refuge for thinkers and dreamers. In that serene environment, surrounded by mountains and lakes, Schrödinger found both solitude and inspiration. His lectures attracted students from across Europe, not only because of his knowledge, but because of the passion with which he spoke. He had the ability to make abstract concepts come alive, to turn mathematics into a living story. But it was not teaching alone that occupied his mind. He began to immerse himself in the mysteries of atomic structure, following the developments that had emerged from experiments with radiation and electrons. Niels Bohr's model of the atom, with electrons orbiting the nucleus like planets around the sun, had been accepted widely. Yet, something about it felt unsatisfying to Schrödinger. The model explained energy levels but not the continuous nature of motion. He wondered if the behavior of electrons might be better described not by discrete orbits, but by continuous waves. This idea did not come to him all at once. It evolved gradually, through years of reflection and dialogue with the works of others. The French physicist Louis de Broglie had recently proposed that matter, like light, could behave as both wave and particle. Schrödinger read de Broglie's papers with fascination. Here was a concept that resonated deeply with his own intuition. The idea that the universe was not built from tiny, separate objects but from oscillating patterns of energy. To Schrödinger, this was poetry in motion, the same poetry he had glimpsed in the rhythm of light and sound as a child. Around this time, Schrödinger began to spend long hours alone, sometimes retreating to mountain lodges or quiet villages. He would take notebooks and little else, letting his thoughts wander freely. It was during one such period of solitude in the Swiss Alps, in late 1925, that inspiration struck. He began to develop a mathematical framework that could describe de Broglie's waves, a framework that would soon become known as wave mechanics. He worked tirelessly, driven by a sense that he was on the verge of something extraordinary. His mind moved between intuition and calculation, between vision and verification. Schrödinger's influences were not limited to science alone. Throughout his life, he had been captivated by philosophy, particularly by the ideas of Schopenhauer, Spinoza, and the Eastern mystics. Schopenhauer's concept of the world as a unified will deeply affected him. It suggested that beneath the diversity of phenomena lay a single, underlying reality. Schrödinger saw in this the same truth that physics was beginning to reveal, that the multiplicity of particles might be nothing more than expressions of one fundamental wave. He also read the Upanishads, the ancient Indian scriptures that spoke of the unity of the self and the cosmos. Their insight that the Atman is Brahman, that the individual and the universal are one, resonated with his own view of the physical world. He once wrote that these ancient ideas contained a wisdom that modern science was only beginning to rediscover. This fusion of philosophy and physics became the defining feature of Schrödinger's journey. He did not see himself merely as a scientist analyzing equations, he saw himself as an explorer of existence. His influences came from every direction, from mathematics and metaphysics, from poetry and nature. He believed that true understanding could not be achieved by dividing knowledge into compartments. It required seeing the whole picture. This holistic vision was what allowed him to approach physics in a way that was both rigorous and imaginative. By the mid-1920s, the scientific world was in turmoil. Werner Heisenberg had developed matrix mechanics, a strange and abstract formulation of quantum theory that could predict results, but offered no visual picture of how nature worked. Schrödinger respected Heisenberg's mathematical skill, but felt uneasy with the approach. He longed for clarity, for something that could be visualized and understood intuitively. His mind sought images, analogies, waves, the continuous flow of nature rather than the sharp discontinuities of matrices. In this intellectual tension, Schrödinger's individuality shone. Where others saw mathematics as a tool, he saw it as art, an expression of nature's harmony. The influences that had shaped him, his father's curiosity, Boltzmann's statistics, Einstein's relativity, de Broglie's waves, Schopenhauer's philosophy, all converged in his consciousness. He began to see wave mechanics not just as a theory, but as a bridge between science and philosophy, between determinism and uncertainty, between the physical and the metaphysical. When he finally published his papers on wave mechanics in 1926, the world of physics was transformed. But those equations were not born in a vacuum. They were the flowering of years of reflection, of education, of influence. The path that had begun in the classrooms of Vienna, passed through the tragedies of war, and matured in the calm of Zurich, had now reached its first great summit. Schrödinger had become not just a physicist, but a philosopher of nature, one whose equations sang of unity rather than fragmentation. At this stage of his journey, Schrödinger stood at the intersection of science and spirit. He had discovered that the same mathematical beauty that described waves of light could also describe the invisible patterns of matter. The discovery was revolutionary, but for him, it was also deeply personal. He felt that he had glimpsed the underlying order of the cosmos, the same order that poets and philosophers had spoken of in metaphors for centuries. His path into theoretical physics was never merely about solving problems, it was about finding meaning in the vast, mysterious dance of existence. And as he continued to walk this path, Schrödinger would soon discover that the deeper one peers into reality, the more it begins to question the nature of observation itself. A realization that would lead him to his most famous thought experiment, the quantum cat. But before that moment of paradox and fame, his journey through theoretical physics had already defined him. As a man who stood between worlds, uniting science and philosophy, precision and imagination, logic and wonder, into one continuous wave of thought. As Schrödinger stepped into the heart of the 20th century, the winds of change in science were sweeping faster than ever before. The old pillars of Newtonian certainty were cracking under the weight of new discoveries. The atom, once thought to be an indivisible unit of matter, was no longer a solid sphere but a mysterious space of probabilities and energies. The rise of quantum theory, initiated by Max Planck and soon expanded by Albert Einstein's photon theory, had begun to challenge the very way humans understood light, energy, and existence itself. It was in this scientific storm that Erwin Schrödinger found his calling, not merely to observe, but to interpret, to give form and harmony to the chaos of new ideas. He stood at the threshold of two worlds, one ruled by the predictable laws of classical mechanics, and the other by the strange, almost mystical rules of the quantum realm. The Vienna of Schrödinger's youth had given him a foundation in both rigorous logic and poetic imagination. But as he matured, the influences around him expanded. He was drawn deeply to the philosophical currents of the age, works of Spinoza, Schopenhauer, and the Eastern philosophies that spoke of unity, illusion, and consciousness. These ideas became the silent undercurrent of his scientific vision. To Schrödinger, the pursuit of physics was not merely about numbers or equations, it was a quest to understand the soul of nature itself. He once wrote that the task of science was not to tear nature apart, but to understand her harmony. This sentiment would guide him as he ventured into the uncharted depths of the quantum world. By the early 1920s, quantum theory was in turmoil. Planck's quantization of energy and Einstein's work on the photoelectric effect had opened new doors, but no one could yet explain how or why the microscopic world behaved so differently from the macroscopic. Niels Bohr had introduced his model of the atom with quantized orbits, and Werner Heisenberg had begun developing his matrix mechanics, a mathematical framework that was powerful but abstract, lacking intuitive meaning. Many physicists struggled to connect these new ideas to the visible, tangible universe. Schrödinger, with his deep love of continuity and waves, believed that nature could not be as fragmented as others suggested. He sought a model that would bring elegance back into the description of atoms, something that could reconcile the strange quantum jumps with the smooth order of mathematics. During a period of personal difficulty and reflection, Schrödinger retreated to the mountains of Arosa, Switzerland in 1925. There, surrounded by silence and snow, he began the work that would change physics forever. Inspired by the idea of de Broglie's matter waves, the notion that every particle could also be described as a wave, Schrödinger asked himself, what if electrons, instead of being particles moving in orbits, were standing waves surrounding the nucleus? Could the patterns of these waves explain the quantized energy levels of atoms that Bohr and Planck had described? In a burst of creative clarity, Schrödinger began to derive a mathematical equation that could describe such waves. It was a synthesis of physics and art, lines of symbols that spoke a language deeper than any words. By early 1926, he had formulated what would become one of the most famous equations in science, the Schrödinger equation. This equation was not just a formula, it was a revelation. It described how the wave function, a mathematical expression of a quantum system, evolved over time. With it, physicists could calculate the energy states of electrons in atoms, predict the structure of molecules, and even understand the behavior of light and matter on scales smaller than imagination could reach. When Schrödinger presented his work to the scientific community, it was received with astonishment. Here, at last, was a picture of the quantum world that seemed continuous, logical, and beautiful. His wave mechanics provided an alternative to Heisenberg's matrix mechanics, and the two soon proved mathematically equivalent, different languages describing the same mysterious reality. But Schrödinger's interpretation was far more visual and intuitive, appealing to those who still longed for a tangible model of the atom. His waves seemed to restore order to the quantum chaos, yet at the same time, they opened the door to new questions that would haunt physics for generations. Schrödinger's rise to prominence was meteoric. Universities invited him to lecture, and his papers became essential reading for every physicist exploring the quantum frontier. Yet fame did not bring satisfaction. Schrödinger was deeply aware that the quantum world he helped describe was strange beyond comprehension. The wave function, though powerful, did not tell him what was waving, or where the boundary between possibility and reality truly lay. He was both the architect of a new understanding and the philosopher questioning its foundation. To him, quantum mechanics was not merely about particles and energies, it was a mirror reflecting the limits of human perception. As his reputation grew, Schrödinger found himself in the company of the greatest scientific minds of his time: Einstein, Bohr, Heisenberg, Pauli, and Dirac. These were not merely scientists, they were explorers of the invisible, each with a different vision of truth. Einstein admired Schrödinger's pursuit of clarity, but both men were skeptical of the probabilistic interpretation that others were embracing. They believed that beneath the apparent randomness of quantum events, there must exist a deeper order, a hidden logic that the current theories could not yet see. Bohr and Heisenberg, on the other hand, insisted that quantum mechanics was complete, that reality itself was defined only when observed. Schrödinger found this deeply troubling. The idea that the universe required an observer to exist seemed absurd to him. He believed that the waves he described were real, not just mathematical constructs waiting for observation to make them meaningful. These debates would shape the course of modern physics, and Schrödinger's role in them was both central and complex. Though he helped build the foundation of quantum theory, he also became one of its sharpest critics. His correspondence with Einstein was filled with discussions about determinism, reality, and the nature of existence. Together, they questioned whether the universe truly operated by chance, or whether the randomness of quantum mechanics was simply a sign that something was missing from the picture. This philosophical tension, between the elegance of his mathematics and the discomfort of its implications, would follow Schrödinger for the rest of his life. But while these intellectual battles raged, the impact of Schrödinger's work was undeniable. His equation explained the structure of the hydrogen atom with remarkable precision, predicted the spectral lines observed in experiments, and laid the groundwork for quantum chemistry, solid-state physics, and even modern electronics. every transistor, every laser, every quantum computer that exists today owes a part of its existence to the equation he wrote in those snowy mountains of Arosa. The ripples of his insight spread far beyond the laboratory, influencing philosophy, technology, and the very way we understand reality. Despite his scientific triumphs, Schrödinger remained a restless thinker. He was never satisfied with narrow specialization. He wrote essays on color perception, on life and consciousness, and on the unity of mind and matter. His interdisciplinary curiosity made him a bridge between science and the humanities, between the measurable and the mysterious. He believed that the essence of existence could not be confined to equations alone, that there was a living consciousness underlying the universe, a single stream of awareness flowing through all forms of life. His reading of ancient Indian philosophy, particularly the Vedanta, resonated with his vision of a universe without true separation between observer and observed. In his lectures and writings, Schrödinger often spoke about the continuity of life and the illusion of individuality. He argued that the consciousness that looks through one person's eyes is not fundamentally different from that of another. This perspective, deeply influenced by both science and spirituality, reflected his belief that knowledge of the universe and knowledge of the self were two sides of the same quest. It was a radical view for a physicist, but for Schrödinger, it was the only way to reconcile the strange truths of quantum theory with the intuitive experience of being alive. As his life moved forward, Schrödinger's journey became not only one of science but of meaning. He saw the unfolding story of quantum mechanics as a metaphor for the human condition, the dance between certainty and uncertainty, the search for order and chaos, the interplay of light and shadow. His contributions to physics changed the world, but his reflections on existence gave those contributions a soul. He was not content to be remembered as a man who wrote an equation. He wanted to be remembered as someone who dared to imagine the deeper reality behind the symbols. In the grand story of human discovery, Erwin Schrödinger stands as both a scientist and a philosopher, a dreamer who saw the universe as a web of waves and consciousness intertwined. His journey into theoretical physics was not just a march of intellect, but a voyage of imagination. He walked through the boundaries of knowledge, questioning every assumption and illuminating every paradox. Through his mind, the abstract became beautiful, the mysterious became tangible, and the invisible became real. Even today, when physicists solve his equation or invoke his name, they are not merely doing calculations. They are continuing the same quest that guided him, the timeless search to understand the hidden rhythm of the universe. In the early 1920s, physics was undergoing an intellectual revolution unlike anything humanity had ever seen. The discoveries of the preceding decades had dismantled the comfortable certainties of classical science. Newton's laws, which once seemed to explain every motion in the universe, were proving inadequate in the strange, invisible world of the atom. The steady and predictable view of reality had fractured, replaced by mysteries that defied logic. Energy was no longer continuous but came in discrete packets, quanta, as Planck had revealed. Light, which had long been understood as a wave, also behaved as if it were made of particles, as Einstein had boldly suggested. Matter itself seemed to blur the line between wave and particle, and the old ways of describing nature no longer worked. Into this turbulence stepped Erwin Schrödinger, a thinker whose mind was as much poetic as it was mathematical, ready to weave the chaos of new discoveries into a single, harmonious pattern. Schrödinger's journey toward wave mechanics began not with an experiment, but with a thought, a desire for unity in understanding. He had grown increasingly dissatisfied with the abstract and fragmented approaches that dominated physics after Planck and Bohr. While others tried to describe the quantum world using statistical probabilities and quantum jumps, Schrödinger longed for something smoother, something that reflected the continuity he believed nature must possess. To him, the world could not truly be built on discontinuous leaps and invisible randomness. There had to be an underlying order, a rhythm beneath the apparent chaos. His instincts were both scientific and aesthetic. He wanted equations that not only worked but sang with beauty. It was around 1925 when a spark lit his imagination. In France, a young physicist named Louis de Broglie had proposed a daring idea that if light, once thought to be purely a wave, could also behave like a particle, then perhaps matter, long considered particulate, could also behave like a wave. This symmetry between light and matter fascinated Schrödinger. De Broglie's hypothesis suggested that every particle, like an electron, could be associated with a wave, the length of which depended on its momentum. It was a radical notion, but it resonated deeply with Schrödinger's intuition about the continuity of nature. For him, this was not just a mathematical curiosity, it was a clue to something fundamental about reality. Schrödinger began to ask himself a question that would change physics forever. If matter is a wave, what equation governs its motion? Every wave in physics, from sound to water to light, follows a mathematical law that describes how it propagates. Could there be a similar law for the waves of matter? He began to imagine electrons not as tiny particles orbiting the nucleus, but as standing waves, continuous vibrations surrounding the atomic core, like sound resonating in a musical instrument. The atom, in his mind, became a kind of cosmic orchestra, each electron occupying a specific pattern of vibration, each energy level corresponding to a distinct frequency of standing waves. During the winter of 1925, Schrödinger retreated to the quiet mountain resort of Arosa in Switzerland. He was physically exhausted and emotionally troubled, but intellectually aflame. The world outside was blanketed in snow, and in the isolation of that white silence, his mind turned inward. There, surrounded by nature's stillness, he began to build the mathematical framework that would become his greatest contribution to science. Over long nights and days, he filled his notebooks with equations, experimenting with different forms until the patterns began to take shape. His goal was simple in appearance but profound in depth: to find a wave equation that could describe how the matter waves of electrons behaved in an atom. It was a time of both struggle and exhilaration. Schrödinger tested his ideas against known experimental results, particularly the spectral lines of hydrogen, the fingerprint patterns of light emitted by atoms. These lines were known with extraordinary precision, and any successful theory would have to explain them. Classical physics had failed to do so, and while Bohr's quantum model could reproduce them, it relied on arbitrary quantization rules that lacked deeper justification. Schrödinger's intuition told him that if electrons were standing waves, their allowed energy levels would emerge naturally from the mathematics, without the need for artificial constraints. After weeks of effort, a breakthrough came. Schrödinger derived a differential equation that described the evolution of a wave function, a mathematical entity representing the quantum state of a system. This equation was not based on guesswork. It emerged from first principles, using the well-established tools of classical mechanics, but transforming them into a new domain. The result was elegant and universal, capable of describing the motion of any quantum system. Schrödinger's wave equation had been born. It was a quiet moment of triumph, the culmination of years of thought and struggle, yet its implications were staggering. With a single mathematical expression, Schrödinger had captured the essence of the quantum world, not as a collection of random jumps, but as a sea of continuous waves unfolding through time. When Schrödinger published his work in 1926, it electrified the scientific community. Physicists had been wrestling with Heisenberg's newly introduced matrix mechanics, a complex and abstract framework that worked mathematically but offered no clear picture of what was happening inside the atom. Schrödinger's approach, by contrast, was intuitive, visual, and grounded in familiar concepts. His waves could be plotted, imagined, and visualized. They seemed to offer a return to the clarity that science had lost in its plunge into abstraction. To many, it felt like a rescue, a bridge back to the physical reality they could understand. The equation itself was deceptively simple in form, yet infinitely rich in meaning. It stated that the energy of a quantum system is related to the curvature of its wave function. In essence, that the behavior of matter is governed by the shapes and vibrations of invisible waves. Solving the equation for hydrogen, Schrödinger found that the allowed energy levels matched perfectly with Bohr's earlier results. What had once seemed like arbitrary quantization now appeared as a natural consequence of wave patterns. The orbits of Bohr's model dissolved into probability clouds, regions where the electron was most likely to be found. The atom was no longer a miniature solar system, but a shimmering pattern of standing waves. Schrödinger's triumph was not merely mathematical, it was philosophical. His equation suggested that the universe might be woven from waves of probability rather than particles of matter, that reality itself could be seen as a kind of cosmic music, its structure defined by interference, resonance, and harmony. The boundaries between material and immaterial, between energy and existence, began to blur. The more one solved the equation, the more it seemed to describe not just particles, but the underlying order of the cosmos. In the months that followed, Schrödinger expanded his theory, applying it to increasingly complex systems. He introduced the concept of the wave function, denoted by the Greek letter ψ, as the mathematical representation of a quantum state. The wave function contained everything that could be known about a system, encoding the probabilities of its possible states. Yet Schrödinger himself hesitated to interpret as a mere probability. To him it represented something physically real, a continuous field of energy or matter that existed independently of observation. This view would place him at odds with others, especially Bohr and Heisenberg, who soon developed the Copenhagen interpretation. The idea that the wave function only represented potential outcomes, not actual reality, until observed. But at this early stage, Schrödinger's focus was not on philosophical debates, but on the beauty of the mathematics itself. The more he explored, the more he realized that his equation was capable of describing an astonishing range of physical phenomena, from the structure of atoms to the behavior of molecules and even the vibrational modes of crystals. Wave mechanics was not a narrow theory, but a universal language of nature. It offered a sense of unity that resonated deeply with Schrödinger's lifelong search for order and meaning. The publication of his 4 landmark papers in 1926 marked a new era in physics. Together, they laid the foundation for what became known as wave mechanics, standing alongside Heisenberg's matrix mechanics as one of the 2 pillars of quantum theory. Though the 2 approaches appeared different, Schrödinger later demonstrated that they were mathematically equivalent, 2 sides of the same coin. Yet the contrast in their interpretations could not have been sharper. Heisenberg's view reduced reality to discrete measurable quantities, while Schrödinger's vision emphasized the continuous, the fluid, and the interconnected. It was as if 2 different philosophies of nature had emerged from the same mathematics, one based on uncertainty, the other on harmony. For Schrödinger, the discovery was not simply a scientific achievement, it was a deeply human moment, a realization that the language of waves could describe the invisible architecture of existence. He often spoke of his work not with pride but with wonder, as if he himself were merely a witness to something greater than his own intellect. The equation had come to him not as a conquest, but as a revelation, a glimpse into the hidden symphony of the universe. In the glow of his success, Schrödinger's life changed dramatically. Invitations poured in from across Europe. Universities and scientific institutions sought his presence, eager to hear from the man whose equation had illuminated the quantum world. Yet behind his calm demeanor, Schrödinger remained introspective. He knew that his theory, while powerful, had opened more questions than it had answered. What was the true nature of the wave function? What did it mean for something to exist as a wave of probability? And how could one reconcile the smooth determinism of his equation with the randomness implied by observation? These questions would soon become the heart of the quantum debate, and Schrödinger would find himself not only a pioneer but also a philosopher, and at times a skeptic of his own creation. The world, however, had already changed. The birth of wave mechanics marked a turning point in human thought. For the first time, scientists had a tool to describe the subatomic realm with astonishing precision. The atom was no longer a mystery but a system that could be mathematically understood. The structure of matter, the behavior of electrons, the properties of light, all could be traced back to the patterns of invisible waves described by Schrödinger's equation. From chemistry to electronics, from the design of new materials to the development of quantum technology, the ripples of his insight would spread through every field of science. Yet for Schrödinger himself, the story was far from over. The beauty of his equation was undeniable, but its meaning remained elusive. The more he studied it, the more he realized that it described a world unlike any humans had ever imagined, a world where particles were not things but possibilities, where boundaries dissolved, and where reality itself seemed to exist in superposition, both real and unreal, until observed. It was a revelation that would lead him to the next great chapter of his life, where mathematics would give way to paradox, and imagination would give birth to one of the most famous thought experiments in history. The emergence of Schrödinger's wave mechanics did not merely revolutionize physics, it redefined humanity's understanding of what reality itself could mean. The more his ideas spread, the more they began to challenge not only science but philosophy, logic, and even perception. In the early days following his discovery, Schrödinger stood at the center of a new world, admired and questioned in equal measure. His equation was beautiful and precise, but it described a universe so strange that even he could barely grasp its full implications. The equation seemed to whisper of a reality beneath appearances, a hidden order beneath randomness, and yet it refused to yield its true meaning easily. Schrödinger's equation was, in essence, a bridge between the known and the unknowable. It could predict, with almost miraculous accuracy, how electrons behaved within atoms or how particles interacted in tiny systems. But what did the wave in his wave mechanics truly represent? Was it a physical wave spreading through space, or was it a wave of knowledge, a mathematical symbol of what we could know about the system? This question quickly became the center of fierce debate. Many physicists, including Bohr and Heisenberg, embraced the view that the wave function represented probabilities, that it did not describe something real, but rather our limited knowledge of a quantum system before measurement. To them, reality existed only in the moment of observation. But Schrödinger could not accept this. To him, the wave function was a real, physical entity. The world, he believed, must exist independently of human observers. The conflict between these interpretations was not merely a scientific disagreement. It was a philosophical confrontation between two visions of the universe. On one side stood the Copenhagen school, led by Bohr, which held that nature was fundamentally indeterminate. On the other stood Schrödinger and Einstein, who insisted that nature must have a definite existence even when unobserved. Schrödinger's equation gave both sides their ground. It allowed for prediction, but it also hid within it a mystery. The collapse of the wave function. When no one was looking, the quantum world was described by smooth, evolving waves. But when an observation occurred, those waves appeared to collapse into a single, definite outcome. To Schrödinger, this collapse was an unacceptable discontinuity, an intrusion of human consciousness into the natural order. He longed for a vision of physics that remained objective and continuous, one that would not depend on whether anyone was watching. As he wrestled with these implications, Schrödinger's fame grew rapidly. He accepted a professorship in Zurich, where his lectures attracted physicists from across Europe. He was charming, eloquent, and deeply thoughtful, a man who combined mathematical rigor with philosophical depth. His students recalled his ability to describe complex ideas with poetic clarity, as though he were painting with mathematics rather than writing it. But behind the calm of his voice, His mind was still at war with itself. He had given the world a tool of immense power, yet he was uneasy about what it revealed. The quantum realm, with its probabilities and uncertainties, seemed to defy the very logic of nature. How could something exist as a wave of potential, then suddenly become a particle when observed? How could reality depend on observation, when for centuries science had assumed that the universe existed independently of our gaze? In letters exchanged with Albert Einstein, Schrödinger often voiced his frustration. Einstein, too, was troubled by the direction in which quantum mechanics was heading. God does not play dice, Einstein famously declared, and Schrödinger agreed. The two men shared a conviction that the apparent randomness of the quantum world was an illusion born of incomplete knowledge. There had to be a deeper, hidden layer of reality, a level of order still unseen. Their conversations became legendary. Philosophical duels fought with equations and metaphors rather than weapons. Both men admired the precision of quantum mechanics but refused to accept its philosophical implications. For Schrödinger, it was as if the theory had outgrown its own meaning. It worked perfectly, yet it no longer explained what was real. Despite these inner tensions, the practical success of wave mechanics was undeniable. It became the foundation upon which chemists, physicists, and engineers built the future. The equation that Schrödinger derived in solitude now governed the design of everything from semiconductors to lasers, from superconductors to quantum computers. It was the mathematical heartbeat of the modern world. Each solution to his equation revealed new insights into the hidden architecture of matter, predicting how electrons formed bonds, how atoms emitted light, and how energy moved across the invisible fabric of space. Even those who disagreed with Schrödinger's interpretation had to admit the unparalleled power of his work. Yet Schrödinger's thoughts wandered far beyond the laboratory. He was haunted by the philosophical question of what the wave equation truly meant. If it described probabilities, then what was it that existed before observation? Was the world itself a kind of dream, real only when observed? These questions blurred the line between physics and metaphysics, pulling Schrödinger into a deeper exploration of existence itself. His mind, always a fusion of science and philosophy, began to look for parallels between quantum theory and the ancient wisdom of the East. He read deeply in Hindu and Buddhist philosophy, finding in their texts echoes of his own struggles with unity and perception. The Vedantic idea that all consciousness is one, that the self and the universe are inseparable, resonated deeply with his vision of the wave function as a continuous field, connecting all things. To him, perhaps the observer was not external to the world but part of it, another wave within the same infinite ocean. In those years, Schrödinger began to see his equation as more than a scientific tool. It became a metaphor for existence itself, a symbol of the relationship between possibility and reality, between the seen and the unseen. Every wave function represented not just a particle, but a spectrum of potentialities, a dance of probabilities that only resolved into the definite when experienced. The physical world, in this sense, was not fixed but fluid, not solid but symphonic. Everything that existed was a pattern of interference and resonance within a grand cosmic field. In this view, reality was less like a machine and more like a piece of music, flowing, interconnected, and alive. But the world of science is not kind to philosophy. Schrödinger's poetic vision often clashed with the pragmatic minds of his contemporaries. Bohr, Heisenberg, and Pauli, the architects of the Copenhagen interpretation, saw his insistence on physical waves as outdated romanticism. They argued that quantum theory was not about what is, but about what can be known. For them, the wave function's meaning ended at the act of measurement. To Schrödinger, this was an abdication of science's true purpose, to describe nature as it really is, not merely as it appears when measured. He refused to believe that the universe depended on human consciousness to exist. To challenge this idea, he would soon conceive one of the most famous thought experiments in the history of science. An imaginative story, that would expose the absurdity of interpreting quantum mechanics purely in terms of observation. But before that cat was imagined, Schrödinger's equation had already achieved immortality. The world continued to change around him. The 1930s brought not only scientific progress but political chaos. Europe was slipping toward darkness, and the freedom of thought that had nourished the great scientific revolutions was under threat. Schrödinger's life, like many of his colleagues, was caught in the crosswinds of history. Yet even in exile and uncertainty, his equation remained his anchor, a reminder that the universe still followed patterns of order and beauty, even as human civilization faltered. His writings from this period reflected both scientific rigor and philosophical depth. He began to merge his understanding of quantum mechanics with his thoughts on biology and consciousness, seeking a unified vision of life itself. Schrödinger's wave mechanics, though born from the study of electrons, soon became the language of all things microscopic. The principles that governed the atom were found to apply to molecules, to chemical reactions, even to the processes of life. In 1944, years after his initial discoveries, he wrote What is Life?, a profound essay exploring how quantum principles might explain the stability and order of living organisms. In it, he argued that life's structure must rest on molecular laws governed by quantum mechanics, an idea that would later inspire the discovery of DNA's double helix by Watson and Crick. The wave he had set in motion in the 1920s had grown into a tidal force, reshaping every field it touched. Looking back, it is almost impossible to imagine modern science without Schrödinger's wave equation. It became the grammar of the quantum world, the silent logic behind everything from atomic clocks to nanotechnology. Yet for Schrödinger himself, the equation remained an enigma. It was both a triumph and a riddle, a key that opened doors but left the rooms half lit. He could describe how the universe behaved, but not why it behaved that way. He could calculate probabilities, but he longed for certainty. And in that longing, he remained forever the philosopher, questioning the foundations of his own discovery. The birth of wave mechanics was not just a scientific event, it was a turning point in human consciousness. It forced mankind to confront a universe where certainty was an illusion, where matter was not solid but vibrating patterns of probability, and where observation itself played a role in shaping reality. Schrödinger had given us the language to describe this world, but he also gave us the humility to admit that we did not yet understand it. In his wave equation lay both the promise of knowledge and the reminder of mystery. Even today, nearly a century after its creation, the Schrödinger equation stands at the heart of quantum theory. Its symbols appear on chalkboards, computer screens, and spacecraft navigation systems, quietly guiding humanity's exploration of the cosmos. But beyond its mathematical power lies the deeper legacy of the man who conceived it. A mind that sought not just to calculate, but to comprehend. Erwin Schrödinger did not merely discover a law of physics, he revealed a philosophy of existence. Through waves and equations, he taught the world that reality is not a static structure, but an unfolding process, fluid, connected, and alive with possibility. And though he would later challenge his own theory with a cat that was both alive and dead, his legacy remains one of harmony. The harmony of thought, imagination, and nature united through the language of mathematics. The birth of wave mechanics was not only the birth of a new science, but the birth of a new way of seeing the universe as a symphony of waves, each note a possibility, each equation a song written in the silent music of existence. The story of Schrödinger's cat began not as a joke, but as a protest, a sharp intellectual rebellion against the interpretation of quantum mechanics that dominated his time. By the early 1930s, Schrödinger had grown increasingly dissatisfied with the Copenhagen school, led by Niels Bohr and Werner Heisenberg. They claimed that quantum particles did not possess definite properties until they were observed, and that the act of measurement itself forced nature to choose an outcome. To Schrödinger, this sounded absurd. The universe, he believed, must exist independently of human observation. Reality, he thought, cannot flicker in and out of existence simply because someone looks at it. And so in 1935, with a blend of wit and philosophical depth, he devised a thought experiment that would expose this absurdity, the now legendary paradox of Schrödinger's cat. He imagined a sealed box containing a cat, a small amount of radioactive material, a Geiger counter, a vial of poison, and a hammer mechanism. The setup was simple yet horrifyingly elegant. If one of the radioactive atoms decayed within a set time, the counter would trigger the hammer, breaking the vial and releasing the poison, killing the cat. If no decay occurred, the cat would live. According to quantum mechanics, until the box was opened and observed, the atom existed in a superposition, both decayed and not decayed at the same time. But if the atom was in two states at once, then so too was the cat. The result was a cat that was simultaneously alive and dead, a creature suspended between two contradictory realities until an observer intervened. Schrödinger did not propose this scenario to endorse it, but to ridicule it. He wanted to show how ridiculous it was to apply quantum theory's rules of uncertainty to everyday, macroscopic objects. For him, the cat paradox was a mirror held up to the face of modern physics, reflecting the confusion that arises when human observation is treated as a fundamental force of nature. The image of the cat was powerful because it was familiar. Everyone could imagine a living being trapped in that box, its fate entangled with the invisible laws of the quantum world. The thought experiment captured, in one striking metaphor, the philosophical crisis at the heart of quantum theory. As soon as Schrödinger introduced the cat, it leaped beyond the pages of academic journals into the imagination of scientists and philosophers alike. Einstein, who shared Schrödinger's discomfort with the indeterminacy of quantum mechanics, applauded the idea. He called it a brilliant illustration of how absurd quantum theory could seem when taken to its logical conclusion. For Einstein, the cat was further proof that quantum mechanics, though accurate in predictions, could not be a complete description of reality. He famously remarked that he liked to think the moon continued to exist even when no one was looking at it, a poetic echo of the same belief that reality should not depend on observation. But Bohr and Heisenberg saw things differently. To them, the cat was not an argument against quantum mechanics, but a perfect example of it. They insisted that until observation occurs, the cat truly exists in both states, that quantum indeterminacy applies universally, even to living creatures. Only when someone opens the box does the wave function collapse, forcing nature to reveal a single outcome. This debate between Schrödinger and Bohr became one of the most profound intellectual duels of the 20th century. It was not just about physics, it was about the nature of reality itself. For the rest of his life, Schrödinger remained fascinated by the paradox he had created. Though he had intended it as a critique, the cat soon took on a life of its own, symbolizing the strange, counterintuitive world of quantum mechanics. It became the ultimate metaphor for uncertainty, for the coexistence of possibilities before reality makes its choice. Philosophers, artists, and writers would later seize upon it as a symbol of human existence, the fragile balance between life and death, the tension between what is and what could be. Even in modern times, the thought experiment continues to inspire new discussions, from quantum computing to consciousness studies, where the act of observation once again plays a mysterious role. Schrödinger's cat stands today as one of the most haunting and enduring images in all of science. In its imagined box lies a universe where logic bends, where existence itself is fluid, and where the simple act of looking can alter the fate of the world within. Schrödinger had sought to expose the strangeness of quantum mechanics. Instead, he revealed the strangeness of reality itself. The cat remains both alive and dead in the collective imagination, a reminder that the universe we inhabit is not as solid, predictable, or separate from us as it seems. Through this paradox, Schrödinger gave voice to the deepest question of all, not just about physics, but about the nature of being. What does it mean to exist before we are observed? As the years passed, Erwin Schrödinger's mind began to wander beyond the boundaries of physics. He had opened the door to the quantum world, but what he found there did not satisfy him completely. He longed for something deeper, a unifying truth that could link the strange, mathematical elegance of quantum theory with the organic complexity of life itself. The mysteries of the atom had already been exposed, but the mystery of the living cell remained untouched. What he asked allowed life to sustain its improbable order in a universe ruled by chaos. It was this question that led him to write What is Life?, a book that would become one of the most influential scientific works of the 20th century. Published in 1944, in the midst of a world torn apart by war, Schrödinger's What is Life? Was a quiet, philosophical reflection on the nature of living matter. It was not written in the dense, technical language of physics but in the clear, contemplative tone of a thinker seeking meaning. In it, Schrödinger proposed that living organisms maintain their structure by feeding on negative entropy, a concept that meant they draw order from disorder, resisting the natural tendency toward decay. This idea, simple yet profound, suggested that the principles of thermodynamics and quantum physics might explain not only the motion of particles, but the persistence of life itself. What made Schrödinger's work revolutionary was his daring suggestion that life's secrets lay in the quantum realm. He speculated that the molecules carrying genetic information must be governed by quantum laws, preserving their structure with extraordinary precision. Long before the discovery of DNA's double helix, he imagined a hereditary code script, a molecular pattern capable of storing and transmitting the blueprint of life. This vision inspired a generation of young scientists, including James Watson, Francis Crick, and Maurice Wilkins, who would later uncover the very structure Schrödinger had predicted. Watson once said that reading What is Life? Made him want to become a scientist, and that spark led directly to one of the greatest discoveries in biology. But beyond its scientific influence, the book was also deeply philosophical. Schrödinger was not satisfied with describing the mechanics of life. He wanted to understand its essence. He asked what consciousness was, how individuality arose, and whether the self was truly separate from the world. Drawing on both Western science and Eastern philosophy, he argued that the separation between observer and observed was an illusion. Just as in quantum physics, where the act of observation changes the system, consciousness too might be an inseparable part of reality. He believed that all minds are fragments of a single, unified consciousness, that at the deepest level, life is one. This idea, drawn from the ancient philosophy of Vedanta, resonated deeply with Schrödinger's lifelong quest for unity. For him, science and spirituality were not enemies, but reflections of the same search for truth. He saw in physics the mathematical structure of the universe, and in consciousness its living awareness. In his later writings, he often spoke of a world where these two aspects, matter and mind, are not distinct entities but complementary expressions of one reality. The total number of minds in the universe is one, he wrote. In fact, consciousness is a singular of which the plural is unknown. These words were not meant as poetry, but as the logical conclusion of a scientist who had spent his life tracing the boundaries of knowledge and finding, at every frontier, the reflection of his own awareness. Schrödinger's ideas were far ahead of his time, and many scientists dismissed his philosophical speculations as mystical. But as the decades passed, his questions began to echo again in new fields. Quantum biology, a discipline that explores how quantum effects influence biological systems, owes its origins to his bold imagination. Modern research into photosynthesis, enzyme reactions, and even the navigation of migratory birds has revealed that quantum mechanics may indeed play a role in life's most fundamental processes. In this way, Schrödinger's intuition continues to find new meaning in the 21st century. His exploration of life also reflected a personal longing. After years of intellectual triumphs, he had grown weary of equations alone. He saw that knowledge, though powerful, could not satisfy the human spirit unless it also brought understanding. For him, the universe was not a cold machine, but a living mystery, filled with beauty and consciousness. His writings on life and mind were attempts to bridge the two, to show that science could describe the structure of existence, but only philosophy could reveal its purpose. In the silence between equations and thought, he sought harmony. Even as he aged, Schrödinger's curiosity never dimmed. He continued to write about mind, matter, and the unity of all things, blending scientific reasoning with the wisdom of ancient texts. His students sometimes found his lectures puzzling. One moment he would speak of energy levels in atoms, the next of the Upanishads and the illusion of separateness. But for Schrödinger, there was no contradiction. The same truth, he believed, spoke through both physics and philosophy. To him, the ultimate question was not how the universe worked, but what it meant to be aware of it. By the time of his death in 1961, Schrödinger had become more than a physicist. He was a thinker who had crossed the boundaries between science, philosophy, and spirituality. His journey from wave mechanics to the study of life was a testament to his belief that all knowledge is connected. The cat in the box, the atom, the cell, the consciousness that observes, all were part of one continuous fabric of reality. He had started with equations and ended with existence itself. Today, when scientists explore the quantum world or biologists unravel the mysteries of genetics, they are, in a sense, walking the path Schrödinger first illuminated. His question, "What is life?" remains as vital as ever, echoing not just in laboratories, but in the human heart. For Schrödinger, the answer was not to be found in data or formulas alone, but in the realization that life and consciousness are not accidents of nature. They are the very expression of the universe, becoming aware of itself. In that timeless vision, Erwin Schrödinger's search for truth becomes more than a scientific journey. It becomes a meditation on what it means to be alive. In the twilight years of his life, Erwin Schrödinger's mind remained as restless and curious as it had ever been. Though the world knew him as the father of wave mechanics and the man who imagined the quantum cat, Schrödinger himself saw his work as only part of a much greater journey, a journey toward understanding the ultimate unity behind existence. He had spent his youth unraveling the mysteries of atoms, his middle years probing the essence of life, and now, as he aged, he turned his gaze inward, toward the mystery of consciousness itself. To him, science was no longer just a pursuit of knowledge. It was a mirror reflecting humanity's search for meaning. The deeper he looked into the universe, the more he saw the reflection of mind staring back at him. Schrödinger had always believed that the universe was not a collection of separate things, but a single, interconnected whole. Quantum mechanics, despite its strange and fragmented appearance, had revealed to him the hidden unity beneath all matter. The wave function, with its delicate patterns of probability, seemed to whisper that separation was an illusion, that everything was part of one vast, vibrating reality. This belief guided his later philosophical writings, where he began to weave together the insights of modern physics with the spiritual wisdom of ancient philosophy. He found in the Upanishads and Vedantic texts a language that echoed his own discoveries, the idea that consciousness is not divided among individuals, but is one universal awareness expressing itself through countless forms. To Schrödinger, the self, the I, that each person feels, was not a separate entity, but a temporary manifestation of the same cosmic consciousness. He compared it to waves rising and falling on the surface of the ocean. Each wave appears distinct, yet all are part of the same sea. This was not mysticism for him, but a natural extension of his scientific vision. If all matter is connected through quantum fields, then why should consciousness be any different? The observer and the observed, he reasoned, are not two, they are aspects of one continuous reality that perceives itself through many eyes. Such thoughts placed him far outside the mainstream of physics, but Schrödinger did not care. He had seen too much of the universe's mystery to believe that equations alone could explain it. In these reflections, one can sense both serenity and longing. Schrödinger had lived through 2 world wars, witnessed the rise of totalitarian regimes, and seen science used for both creation and destruction. Yet he never lost faith in the power of thought, nor in the unity of life. To him, the fragmentation of the world, political, cultural, and intellectual, was an illusion born of ignorance. He believed that recognizing our shared consciousness could dissolve the boundaries that divide humanity. He often wrote that the true task of science was not to dominate nature, but to understand it as part of ourselves. Knowledge, he said, should lead to compassion, for in the deepest sense, the observer and the observed are one and the same. In his later lectures, Schrödinger's words took on a lyrical, almost meditative tone. He spoke not only of particles and waves, but of awareness and existence. He suggested that death, too, might be an illusion, that the consciousness we experience is not extinguished, but continues in forms beyond individuality. The total number of minds in the universe is one, he wrote again, a phrase that seemed both poetic and scientific. To him, consciousness was the fundamental reality, the field in which both matter and energy arose. Physics, biology, and philosophy were merely different languages describing the same truth, that the universe is alive, aware, and unified. Even as illness began to claim his strength, Schrödinger continued to write, to think, to question. His mind remained vibrant, filled with curiosity and wonder. In the quiet moments of his final years, he often returned to his earlier discoveries, the equations that had once defined his career, and now saw them in a different light. The wave function was no longer just a mathematical object, but a metaphor for existence itself, the constant interplay between potential and realization, between what could be and what is. In every oscillation of that wave, he sensed the rhythm of life, birth, decay, and renewal, the eternal dance of the universe. His students remembered him as both a scientist and a philosopher, a man who never accepted easy answers. He could be stern and exacting in his scientific discussions, yet gentle and contemplative when speaking of life's mysteries. He believed that knowledge without reflection was empty, and that the true scientist must also be a poet, someone who sees beauty and meaning in the structure of reality. His home in Austria, surrounded by the quiet of the mountains, became a place of solitude and introspection. There, amid nature's stillness, he found peace in the realization that the boundaries between himself and the world were illusions, that consciousness flowed through all things, connecting him to every living being. In his final years, Schrödinger received recognition and honors for his contributions to science. But such accolades meant little to him. What mattered was the enduring mystery that still surrounded existence. He often said that he did not seek answers, only understanding. When he passed away in 1961, the world lost not just a physicist, but a thinker whose vision extended far beyond the laboratory. His legacy was not confined to wave equations or thought experiments. It was a philosophy of unity, a reminder that science and spirit are not opposites but companions in the same journey. Today, Schrödinger's ideas continue to resonate in unexpected places. In neuroscience, artificial intelligence, and quantum consciousness research, his questions about the nature of awareness still echo. The paradoxes he revealed, of observation, superposition, and existence, remain unsolved, reminding us that reality is more mysterious than we can ever imagine. His life stands as a testament to the power of curiosity, the courage to ask questions that bridge science and soul. In the end, Schrödinger's story is not just about physics or philosophy. It is about the human desire to understand who we are. He began by exploring atoms and ended by exploring awareness itself. Between those two journeys lies the story of a man who saw unity where others saw division, who looked at the fabric of the universe and found consciousness woven through its threads. For him, the greatest equation of all was not written on paper, but in the realization that life, mind, and matter are all expressions of one timeless reality, the same wave endlessly unfolding, alive within everything. Erwin Schrödinger's legacy extends far beyond the boundaries of his time. His name lives not only in equations and textbooks, but in the very foundations of modern thought. To understand his legacy is to trace the ripple of a single mind through the ocean of human knowledge. A mind that dared to imagine, question, and unite the fragmented picture of existence. When Schrödinger left the world in 1961, he did not leave behind a closed story. He left a living idea, one that continues to evolve, challenge, and inspire. His equation, simple in form yet infinite in implication, remains at the heart of physics, whispering its truths to generations of scientists who continue to decipher its language. The wave function he conceived still governs the invisible motion of particles, guiding the design of lasers, semiconductors, quantum computers, and technologies that shape the modern world. Every time an electron moves in a circuit or a photon travels through a fiber optic cable, Schrödinger's mathematics quietly operates beneath the surface, unseen yet indispensable. But his legacy reaches even deeper, into the philosophical and cultural imagination of humanity. The thought experiment of Schrödinger's cat has transcended science to become a symbol of paradox and possibility. It appears in art, literature, and popular culture, representing the mystery of uncertainty and the fragile balance between existence and perception. The cat that is both alive and dead at once has become a universal metaphor, not just for quantum physics, but for the human condition itself, where life is a blend of contradictions, choices, and unknowns. Schrödinger had set out to mock the absurdity of interpreting quantum theory too literally, yet the image he created became one of the most powerful expressions of modern philosophy. In that box lies not only the fate of a cat, but the eternal question: is reality something we discover, or something we create by observing it? In the scientific world, Schrödinger's contributions inspired a revolution that continues to unfold. His wave mechanics provided the mathematical foundation for understanding atoms and molecules, but it also opened the door to quantum field theory, quantum chemistry, and condensed matter physics. The structure of materials, the behavior of light, the stability of matter itself, all are governed by the principles that emerged from his work. Without Schrödinger, the digital age, the space age, and the quantum age might never have come to be. The technology that connects continents, explores galaxies, and simulates life on computers owes a silent debt to his equation. Even in the smallest vibrations of atomic clocks that measure time with unimaginable precision, Schrödinger's wave functions resonate, ensuring that every moment humanity records carries a trace of his genius. Yet perhaps his greatest legacy lies not in the practical applications of his discoveries, but in the way he changed how we think about reality. Schrödinger reminded the world that science is not only about prediction, but about understanding. He refused to accept the division between observer and observed, between consciousness and matter. His writings on unity and awareness have influenced philosophers, neuroscientists, and spiritual thinkers alike. In a time when science and spirituality seemed destined to diverge, Schrödinger dared to bridge them, showing that both seek the same truth from different directions. His belief that all consciousness is one, that individuality is an illusion born from perception, continues to inspire discussions in modern philosophy and cognitive science. The very idea of interconnectedness, now echoed in ecology, systems theory, and even artificial intelligence, can be traced back to Schrödinger's vision of a unified universe. In the classrooms and laboratories of today, young scientists still encounter Schrödinger's name early in their studies. They solve his equation, plot its waves, and marvel at its precision. Yet few equations in history have carried such poetry within their symbols. For Schrödinger, mathematics was never cold or mechanical, it was alive, resonant, and filled with beauty. He often said that to understand nature was to hear her music, a harmony of patterns woven through space and time. His work taught the world that even in the smallest scales, there is elegance, order, and mystery. He turned physics into a philosophy of wonder, proving that the pursuit of knowledge can also be an act of reverence. As the 20th century gave way to the 21st, Schrödinger's ideas began to take on new forms. Quantum mechanics, once a theory of the microscopic world, now shapes the future of technology. Quantum computing, teleportation, and cryptography all trace their lineage to his insights. Each new discovery in quantum research is a continuation of the journey he began nearly a century ago. And as scientists push the boundaries of what is possible, Schrödinger's presence lingers, not as a shadow, but as a guiding light. His insistence on unity, coherence, and meaning in a fragmented world remains more relevant than ever. There is something timeless about the way Schrödinger approached existence. He never allowed the boundaries of discipline to limit his curiosity. He was at once a physicist, philosopher, poet, and seeker. He saw the same truth in the equations of atoms and in the verses of the Upanishads. He understood that knowledge without wisdom is incomplete, that the purpose of science is not only to control nature, but to comprehend it as part of ourselves. This belief, radical in its simplicity, continues to echo in every field where the mysteries of consciousness and matter intersect, in an age increasingly defined by technology and data. Schrödinger's vision reminds us to look beyond the surface, to see the living unity that connects all things. In the quiet of history's reflection, Schrödinger stands as one of those rare figures who reshaped not just science, but the story of thought itself. His wave equation transformed the physical world, his cat transformed the philosophical one, and his reflections on life transformed the spiritual landscape of modern science. He showed that the quest for understanding the universe is inseparable from the quest to understand ourselves. Even today, as physicists search for a theory of everything, they are, in spirit, continuing Schrödinger's journey, the search for harmony between the laws of nature and the mystery of consciousness. And so, his legacy endures, not in marble statues or solemn monuments, but in the endless curiosity of minds inspired by his work. Every experiment that probes the quantum world, every question that seeks to unite science and soul, carries the echo of his vision. Erwin Schrödinger's life was a symphony of thought, sometimes dissonant, often profound, always searching for order in the chaos of existence. His wave still travels through time, unseen yet eternal, reminding humanity that the boundaries between life, mind, and matter are but waves in the same infinite sea.